All right. Hello, everyone. Looks like we have our regular stable group of people here. So let's get the lecture started, and we'll start slow, just in case there are a couple of people running late. Okay. So first of all, can everybody hear me well? Can everybody see the shared slides? Awesome. Yeah, so I'll start with a few logistic notes. The homework 2 is due today. So please submit your homework through Gradescope before midnight in order to not use your budget for late homework submissions. Another thing is that we're still in the process of grading the homework 1. My TA Kaiqi is working very hard towards it. It's a tough homework to grade, but he has already finished the like 75% of it, and will release the grades of all the homework on Gradescope, and we'll have that session that Kaiqi collect all your feedback. What are the questions that you guys want him to go over again in his in his office hour, and we'll have a more structured office hour scheduled. And Kaiqi, please remember to collect the feedbacks in terms of which questions that you are supposed to go through in your office hour. Okay, and for those who cannot attend the office hour, so we will consider recording the session, but the format of that session will be a question answering style. Okay, so all right, let's get to the lecture. So this is the 9th lecture of this class. Today we're finally moving to talk about a connection between optimization problems in terms of the duality. Okay, so this is a very elegant part of convex analysis and convex optimization. So let's look forward to it. So quick recap last time. So last time we talked about stochastic gradient methods and stochastic subgradient methods. In particular, we considered the optimization problem of this form that's typically seen in the context of machine learning when you're doing empirical risk minimization, where these FIs are surrogate laws for, say, classification of one of the ICE data point. And it gives some indication whether your classification is correct or not. In the context of statistical estimation, you can think about this FI as a negative log likelihood. And since it's log likelihood, and then this summation form naturally comes from the independence assumption, which factorizes the probability distribution. Okay, so stochastic gradient descent pick a random coordinate ik, and then move along the line of only the direction that's given by the so-called incremental gradient that's evaluated only on this data point ik. Okay, since this is chosen uniformly at random, the key idea of our proof of convergence of stochastic gradient descent is that this incremental gradient is actually an unbiased estimator of the gradient of the objective function. Okay, so SGD is fast in the sense that it saves you on the dependence on M, the size of the data set. So you don't have to go over the entire data set before updating your parameter once. So that can lead to significantly more practical algorithm in practice. The downside, on the other hand, is that SGD is so general that it actually covers a large family of very important problems called stochastic optimization. And if you can solve SGD faster than the given rate 1 over square root of k, or 1 over k for strongly convex objective functions, then that implies that you can break the information theoretic limit. Therefore, the rates that we derived are actually optimal. The downside, on the other hand, is that these rates, 1 over square root of n, 1 over square root of k, is still like a sublinear rate that's really slow. So we talk about whether this is the end of the story, and then commented on a slightly more recent line of work, like starting from like 7-8 years ago, on solving the finite sum problems that and established that the stochastic methods such as stochastic gradient descent and variance based on incremental gradient evaluation can actually be significantly faster on this specific family of problems like these called finite sum. Okay, so we stopped last time before we talk about the last example on another interesting connection of SGD and to regularization. So there's always this intuitive connection that if you run stochastic gradient descent and then you stop early, then that's very similar to regularizing with, say, the like something like a Tikhonov regularization that penalizes the square 2 norm of the objective function of the square 2 norm of the parameter vector with some specific choice of regularization parameter lambda. Okay, so this is the part where we stopped. So let's maybe spend the first couple of minutes going back to there so we can finish that chapter before starting on our discussion on duality. Okay, so well. Okay, so let's head back to the previous lecture first. Okay, so so early stopping says that like we can run either gradient descent or stochastic gradient descent for a small number of iterations and then stop right there. Okay, and this intermediate solution, say x to the k, like is this also a solution to some optimization problem? Like, and what is that optimization problem? So clearly, from our convergence analysis, we know that for gradient descent, f of xk minus of fx star smaller than order of 1 over k. And for SGD, and for SGD, if we add expectation, then we have roughly order, ignoring a possibility of logarithmic terms, 1 over square root of k. Okay, but besides that, like maybe the solution x, the case iteration of the solution makes sense on its own right. Maybe it corresponds to some natural formulation with respect to the regularization. In particular, like if you start with 0, if you initialize at 0, the early stopping can be seen as like a shrinkage towards your initialization. So you prefer your solution to somewhere nearer to your initialization. Okay, so this idea can actually be formalized in various contexts. And instead of doing that, I'm pointing you guys to the references that formally establish the connections. So again, this is a very old idea, and on like convex optimization problem, this can actually be formalized, and these are essentially the core of the idea of like over-parameterization in neural network, and how the regularization and how optimizing a neural network using SGD is implicitly regularizing the neural network. Therefore, it leads to generalization and so on. So there's a more recent line of work on that. So later I will provide some pointers towards that body of work. But today let's focus on the intuition. Okay, so think about solving the logistic regression problem using stochastic gradient descent. Or using gradient descent, the gradient looks like the following. Okay, so we are essentially moving towards a direction that tries to correct your error from the previous iteration. Okay, and it turns out that it turns out that we can like the solution beta to the k is actually very similar to the constrained version of the problem, where you have this additional constraint with t chosen to be exactly the same as the exactly the same as the 2 norm of this the current iterate. Okay, so let's see. Let's compare the sequences of solution over the stochastic gradient descent and the corresponding version where we solve this optimization problem exactly with t chosen to be some specific value. Okay, so what you are seeing on these two figures are what we call the regularization paths. So this corresponds to changing t by increasing t from 0 to something that's larger, right? So like this G is a nonlinear mapping to make the figure look a little bit better, but you can think about these as something that's monotonic or proportional to quantities that looks like that. Okay, so if you compare, so what's on the vertical axis, the different line plot the trajectory of you changing t and what the corresponding optimal solution for that parameter t would be like. Okay, so if you take every snapshot here, so that corresponds to choose t such that beta t satisfies this condition that this 2 norm is smaller than 0.337. And then if you collect all these locations of these lines, then you end up getting the optimal solution corresponding to that choice of t. Okay, so the left-hand side is the exact solution of exact optimal solution of this objective function, and the right-hand side are the corresponding corresponding solution that simply comes out of like one pass algorithm that simply runs gradient descent with very small step sizes. Yeah, so if you compare these two, they're different for sure, but they look very similar to each other. 我在上课，你先下去。这个光盘这里面有这个火车游戏，但这个是让你把答对，这个是你做等数，如果有知道了。Yeah, sorry for the glitch. We're all working at home, so there are challenges, and in particular, my kid is in an age that he's very attached to his dad. So yeah, so teaching can be challenging in these times. Yeah, so arguably, if you think about the computational benefit of formalizing this connection, so this is saying that instead of choosing all these tuning parameters t like one by one and solve each problem for each fixed t to the exact optimal, and then make sense of the corresponding solution beta hat t, and maybe like run cross validation to tune the hyperparameters. You can actually just run a one-pass algorithm by streaming through the data, or running the gradient descent algorithm by keep updating your parameters and then keep track of the entire sequences of solution. And that gives you something that's nearly as good statistically. Okay, so that may save you orders of magnitude computation and makes a problem that's not tractable before tractable on your local laptop, for instance. Okay, so so there's a lot left to be formalized about the previous figure, and like I said, I'll point you guys to corresponding references that formalize this connection between regularization and early stopping in the context of machine learning and also in the context of Convex optimization and statistics. Okay. Okay, let's move to the new lecture. So we're going to be talking about duality. So let's start from a couple of examples to motivate the study of duality. I don't know how many of you have taken like the first course in optimization as an undergrad. So such a course typically focuses on, say, linear and network optimization problems. So a lot of the materials today might already be familiar to you. But I wanted to provide an account to these problems that you might have seen before. So perhaps you've learned linear programs before, but you haven't been able to understand what duality, what the primal, the connection between the primal and dual beyond mechanical, knowing mechanically how to construct them, right? So after today's lecture, the hope is to build intuition about the connection between primal problems and dual problem, and how it is corresponding to maximizing maximizing lower bounds, for instance. Okay, so so take LP for example. So this is an LP in its like a standard standard form. So it's not a, I think, canonical form. So this is not the standard convex optimization form where you need to toggle the direction of these inequalities. Yeah, it's also not the canonical form, because canonical form will only have equalities and things that are greater than the 0, as we will see later. Okay, so for this problem, can we the question is, can we somehow construct a lower bound of the optimization problem? Can we actually just solve this optimization problem by just inspecting it? So clearly, the answer is yes, because this objective function value is the same as a lower bound that we already applied here. So we know that the objective function value is always larger than cannot be infeasible. Therefore, like the answer should be 2. And also we can easily check that there exists a pair of xy such that this 2 is attainable. Therefore, like the optimal solution is 2. Right? But did we just get lucky? Like, how about like other more generic type of linear programs? Can we still do the same thing? Can we find the optimal solution by constructing a lower bound? Okay, let's consider another example. Let's take a look at the example here. Okay, so now like the objective function is different from what we have before, but still we can somehow take the non-negative combinations of all the non-negativity inequality constraints, and then just connect them together so that we can construct a lower bound of the objective function. So what we can do is that we can take the first one, we can multiply this inequality by a factor of 2 on both the left-hand side and right-hand side. Okay, and we can add them up, and that allows us to construct the exact form of the objective criteria. And what this is saying is that this is larger than 2. Again, like it's not difficult to check that this is also like something that can be attained by specific choices of a pair of x, y. Therefore, this lower bound b equals 2 is also tight, right? And that's optimal solution. More generally, is that suppose we have p and q here, so we have an arbitrary linear combination of 2 variables x and y and a set of constraints. What we can do is that we can say that, well, let's try to do the same trick by constructing by scaling these inequalities by something that's non-negative, larger than 0, and cy larger than 0, and then try to somehow match what you get in the objective function value, and then doing the same thing on the right-hand side would imply a lower bound. Okay, so let's do that. So all we need to choose and how these scaling factors are is that a plus b. So a plus b is by collecting all the coefficients of x. So by just summing all this together, we get a plus b times x plus a plus c times y, and we know that by just adding everything up, we know that this is larger than the sum of the right hand side, which is 2a, right? So by enforcing that this a plus b is equal to p and a plus c is equal to q, then this 2a is clearly a valid lower bound that we can construct, right? And by inspection, this is also the optimal solution that we can achieve for this problem. Okay, so to see that this is the best we can do, we can also just directly maximize the lower bound by over the parameters a, b, and c. Okay, so that allows us to construct that allows us to construct this optimization problem, which directly and explicitly maximizes that lower bound. Okay, from the previous example, we know that the lower bound is in the form of 2a, and the conditions that we need to satisfy is a plus b equal to p and a plus c equal to q, and everything being non-negative. So this example gives the essence of a pair of problems that are closely related to each other. One is minimizing some quantities, the other is maximizing maximizing some quantities over a number of variables. We call the problem on the left hand side the primal problem, and the problem on the right hand side the dual problem. It is also to be noted that the dual problem is a canonical form of LP, and the primal problem is a standard form of LP in the sense of convex optimization from our second lecture. Okay. And notice another thing to pay attention to is that the number of dual variables is the same as the number of constraints, inequality constraints in the primal, and the number of and the number of summoneds, like in the most generic form, is the same as the and the number of constraints in the dual variable correspond to the number of variables that comes into the linear combination. Okay, let's maybe try another one. Try another like a more generic problem with an additional equality constraint so that we can make it more general. So take the problem on the left hand side, and let's do the same trick that we did before by first converting everything in the constraints to be something that's larger than 0. So we'll have x larger than 0. We have minus y larger than minus 1. We have 3x plus y equals to 2. And let's multiply the left hand side with a. So minus b and 3c plus cy equals to 2c. Okay, and now let's add everything up. So we get and collect the coefficients of variable x and y. We get a plus 3c times x plus minus b plus c times y, and this is larger than minus I guess 2c minus b. Okay, and then let's put this in the objective function. So this is the lower bound that we try to maximize over these quantities, and this is a lower bound that we try to maximize. And then we want to make sure that this objective function, like the left hand side, correspond to exactly the primal. Therefore, that gives us a constraint a plus 3c equals to p and minus b plus c equals to q. In addition, there are additional conditions that we need so that the direction of these inequalities are not toggle, right? So we require this additional condition that A is larger than 0 and B is larger than 0. So notice that we don't actually require any additional constraint for C. Why is that? And the reason is that this is equality constraint. So you can multiply the left and right hand side with any scalar function without changing it. And therefore, like, we don't actually need a constraint for C. Okay, so there's this interesting symmetry between the private LP, between the primal LP and the dual LP in the sense that like the number of inequality constraint translates into, in the primal, translates into the number of equality constraint translates into the number of non-negative variables, and the number of equality constraints translate into the number of unconstrained variables in the dual LP. Okay, so here's the outline of today's lecture. So we'll continue to talk about the duality in LP with a little bit more generality and a different perspective. We'll give examples of the primal and dual problems, some of the classical popular ones that at least illustrate the points. And then we will move on to generalizing the idea to general convex optimization problems, and then talk about the Lagrange dual optimization problem and how to mechanically like derive it by hand. Then we'll give examples of quadratic programs and supervector machine. So due to the time constraint, I may leave some of these examples like that supervector machine and maximum mean taught us the exercises. We'll go over it, but I'll leave like some details for you guys to work out offline. Okay. And then we'll take a break in between. So we'll take a break after we talk about LP duality. Okay, so let's generalize the examples that we had previously and into the standard LP formula in convex optimization in a matrix vector form. Okay, so NALP can be converted into this form, and so essentially we are taking the any linear combination of this linear system of equation with the coefficients applied to every line of this system of equation, and let's call that coefficient vector U. Okay, and then in order for the inequality to hold, we can also take a linear like non-negative combination of all the rows and columns, so that we can construct like a transformation of that into something else. Let's call that set of coefficients V. Okay, and we know that provided that this V is non-negative, and then adding these two remains valid, like remains negative, right? If you move both B and H to the other side of the equation to make it a standard form. Okay, and then and then what this is and then what this is saying is that if you just collect the terms according to X, like by just combining this term and then add them together, extracting X and get this coefficient vector, you get this vector transpose X. And by moving everything to the other side of the inequality, then you get a lower bound. And provided that this is equal to the objective function value that we're trying to minimize, then this becomes a valid lower bound of the objective criteria. Okay, just collecting everything together. You have these constraints here. You have the non-negativity constraint here. And then you have the lower bound here, and that gives you the dual LP, right? So you don't need to remember anything. So once you have an LP, you can just do this simple exercise and to construct the dual LP like very easily by hand. Okay, a prototypical example of LP primal problems and dual problems in LP is this max flow min cut problem. So it originates from about I think more than 100 years ago when the Soviet Union trying to maximize their throughput on their railway network. You know, as a like communist country, they try to do the central planning of a lot of different things. That also motivates the development of science related to how to control and how to optimize when you have all the resources that are available to you. So what they are trying to build over the large landscape of Russia and Soviet Union is to connect everything via railway, so they can push resources from one point to another in the most efficient fashion. Okay, so you can abstract this problem as a like something that's like a combinatorial problem in graphs, right? So suppose you have a source. This is where the resources are coming from. Then you have a sink or a terminal. That's where like that's where all these resources are going to. Okay, and each edge of this graph denotes a connected railway that can get you from one node to another. Okay, so what is drawn here is a directed acyclic graph. Like generalizations are possible, but let's stick with stack for now. So as in the standard notation of the graph, we have a set of vertices and a set of edges. And these are just completely combinatorial objects. And each edge is denoted by a tuple of two nodes that are connected together. Okay, and moreover, the optimization problem that we're optimizing, the arguments that we're optimizing over is a flow Fij. So this is the like the amount of information that we can push through from node I to node J, or the quantity of the quantity of critical resources that we want to push through from node I to node J. Okay, and and there's also like a set of constraints that's given by Cij, right? So how much you can push through through one particular edge is upper bounded by the capacity of the channel. Okay, so that gives us the non-negativity constraint. You cannot like move a negative amount, since this is one directed edge, and also you cannot move it such that it is over the capacity. And in addition, there's this condition that at every node k, all the edges that are coming into the k and all the edges that are going out of k, they carry like a total total amount of either information or quantity of this stuff that you're trying to get from S to T. Okay, so no node can withhold information or can withhold any resources for itself. Okay, so by formula we can write this down as a linear program. The problem is to maximize the total flows that are going out of S And by this constraint, we also know that all the amount of resources that goes out of the source will end up arriving at the terminal. That's simply implied by the last equality constraints. Okay, and subject to a set of linear equality constraint and a set of inequality constraints that provides a box that this Fij needs to sit in. Okay, so using the trick that we learned just now, we can derive the dual of this problem. So I'll leave that as an exercise. So notice that this is maximizing thing. So instead of finding the lower bound, now we try to take some linear combinations of these constraints to construct a valid upper bound, right? And then we want to minimize that upper bound such that it satisfy minimize that upper bound subject to a constraint that all the coefficients would match with the coefficients that are collected with the linear combination. Okay, so again, so I'll leave the working of this as an exercise. Yeah, to derive this from the previous one. So there's a very related homework question about this that I'll make optional. But yeah, if you work this out, then you more or less have solved that homework question. So so for now, just trust me that the dual of the previous max flow problem is of this format. Okay, so let's inspect it. So we're optimizing over two variables, and the variable b is the dimension of the number of edges, and the variable x has a dimension of the number of vertices. Okay, so so we are minimizing the non-negative like averages, like some like non-negative combinations of the channel capacity Cij. Okay. And with some coefficient, and the coefficients needs to satisfy the condition that Bij plus Xij minus plus Xj minus Xi is larger than 0. So so you can think about this Xj and Xi as as a potential function that at every as a potential function at every vertex, and this Bij needs to be larger than the gap of the potential function at these two nodes, and in addition, like we want the potential function at the source to be 1 and the potential function at the terminal to be 0. Okay, written in this format, this optimization problem is not completely it's not completely interpretable, but let's try adding like additional constraints to this problem to make it more restrictive, and then suddenly it will correspond to an interesting combinatorial problem. Okay, let's in addition like say that constrain the problem such that Xi is either 0 or 1. Rather than allowing Xi to be anything like between 0 and 1, any potential function. Let's just say that this is either 0 or 1 for all vertices, and that partitions, just like the max cut problem that we've seen before, that partitions the graph into two pieces. In the one piece, all the vertices that has Xi equals to 1. The other piece is all the nodes that has Xi equals to 0. Okay, so by our constraint, we know that the source is always in A, and the terminal is always in the set B. Then when this happens, so notice that we are trying to minimize this Bij, Cij. Then since Xi minus Xj is either 0 or 1, depending on how depending on whether Xi Xj are the same or not the same, then this essentially says that we can we can, like, once we figure out what these x are, we can also directly get the solution for Bij. And if I is in A and J is in B, in which case it means that we are cutting through this set, then this Bij is equal to 1. Otherwise, Bij is equal to 0. In other words, so Bij collects all the edges that you have to cut in order to separate the nodes into group A and group B. Okay, so that's a cut problem, and the criteria that we're trying to find the cut problem with is to minimize the sum of the cost. So this is the opposite of the max cut problem, where we try to find the cut that maximizes the cut, and this is about minimizing the cut. It's like a very similar style of problem, but they're both combinatorial, but different from the max cut, which is an NP complete problem. We know that the mean cut can actually be solved very efficiently in polynomial time. Okay. So in fact, like, this claim can be directly seen from what we've derived just now. So notice that the value of the max flow problem, which is an LP, is always smaller than the optimal value of the the dual problem, right? So so this is objective function of the dual problem. We'll call that the LP relaxation of the mean cut by simply dropping that condition of xi needs to be either 0 or 1. And since this is a minimization problem, we are relaxing, then we know that this quantity is smaller than the capacity of the mean cut. So the optimal solution will have a smaller criteria value than the more restricted one that require xi to be either 0 or 1. Okay, so the max flow mean cut theorem, it just turns out that this max flow mean cut theorem says that the max flow and the mean cut actually have exactly the same objective function, and that shows us that serves as a sandwich, and sandwich this optimal value of LP relaxed mean cut in between, and that implies that this inequality are actually true, like with equality for every single problem. Okay, so this is one instance where the primal problem and the dual problem happen to have exactly the same optimal solution, and that's what we call strong duality. In general, in general, the problems might have strict inequality here rather than the thing that holds with equal sign. So this equal, we call this strong duality. Strictly smaller than weak duality. So in this case, like the max flow mean cut theorem implies that the primal and dual LP satisfies strong duality. Okay, so we'll talk about a general condition under which we can establish strong duality for many, so in fact, almost all problems that we care about in practice. Okay, so before that, so let's introduce another perspective on the duality of linear program. So let's start with the standard convex optimization formula of the primal LP, and then try to derive the dual LP in a slightly different way. Okay, so again, so we can think about the problem of constructing the duality. Instead of trying to match the coefficients, we can think about it as just constructing a lower bound by subtracting something away from your current bound that's guaranteed to be. So as long as we can guarantee this term to be to be smaller or equal to 0, then the right hand side is always smaller or equal to the left hand side. Okay, and then we'll call this quantity the so-called Lagrangian. Okay, so how do we ensure that that this condition is satisfied? So that requires us to take u to be take v to be non-negative, and then by the inequality constraints, then we know that this is always non-negative. And this term, since for all the feasible solutions, I highlight feasible, for all the feasible solutions, the ax minus b is always always a 0. Therefore, this term doesn't matter for any u. Okay, so now that we've constructed a valid lower bound for all feasible solutions, then we can write this sequence of inequalities. So we know that the since this is always smaller for every single x, therefore it is therefore suppose we minimize this, this will give us something that's smaller than the optimal criteria value of the primal. And in addition, like if we relax these constraints, then the optimal solution criteria will only become smaller, right? That leads to this inequality. And then we'll call the minimizer that gets rid of this this variable x and parameterized by only u and v. So this is defined in a variational form. So this GUV would be an objective function that we can maximize over variables u and v. Okay, so this is an alternative way of viewing the linear program duality. And as we will see later, and the general form of the duality from convex programs are not too much different. Okay, so for this problem, let's work out precisely what this GUV is like. So let's go to the previous formula, okay, and then try to collect all the terms together. So let's collect all the terms together by grouping them by the coefficients of x, right? So we can get first of all we have c, and we have plus a transpose u, right? And then we have the third term that depends on x. We get plus g transpose v. So these are all the coefficients of x. And then let's collect all the things that doesn't depend on x. So we will have all the terms that doesn't depend on x will be u transpose b, actually minus u transpose b plus v transpose h. Okay, so that's all the things that we need, and notice that we are minimizing this over this x without any constraints, right? Therefore, like provided that this term is not 0, then we can minimize x such that we can choose it to be a direction that's a little bit opposite to this, and shoot it to infinity, and that will give us negative infinity evaluation. Okay, that gives us this leg, right? So GUV is negative infinity if the choice of u and v doesn't satisfy the condition that this coefficient is equal to 0. Okay? If this condition is really equal to 0, then this problem becomes independent to x, right? So then everything that's left is our evaluation of GUV that's parameterized by u and v. Again, like I said, this is a general perspective, and you can use this exactly the same trick of constructing lower bound, constructing the Lagrangian, and solving the variational problem of the of minimizing the Lagrangian to obtain this G that depends only on the dual variables for not just the linear program, but also convex optimization problems and even non-convex ones. Okay, so let's give another quick example before we go to our break. So let's consider the problem of matrix games. So let's say that this is a game matrix. Okay, so this is a game matrix where each coordinate of the matrix gives, like, let's take this example. So this is saying that if player J chooses action M and then player R chooses action 2, then in this case, then J needs to pay R this amount of payoff. Okay, so this is described by a matrix game. So take another example of the rock paper scissors. So rock paper scissors, rock paper scissors, and then you can write down the payoff matrix. So paper trumps rock, therefore this is 1, this is -1. Scissors, rock trumps scissors, so you have 1 and -1 and 1 -1 and everything. Whenever you are a draw, then you get 0. So this is one instance of this game matrix. Okay, so so if you consider mixed strategies, this means that instead of picking just one action, each player can pick an arbitrary probability distribution over the actions. So this means that the player J can choose action I with probability xi, and the corresponding policy of the player R is described by another probability vector yj. Okay, this makes sense, right? So whenever these two people are playing against each other by following these policies, then we can use it to take the average, and then by the definition of probability distributions, we can calculate their payoffs and who's winning and who's losing. In a matrix form, we can write it out explicitly as X transpose Py. Okay, you're multiplying this payoff matrix with a probability on the right, and then another on the left. So everything's symmetric. So one person is trying to maximize this quantity, and the other person is trying to minimize this quantity. Now let's suppose that there are two different situations. The first situation is that J, John von Neumann is giving Ryan a little bit of advantage, right? So J says that, well, I'll tell you how I play, right? And then you can come up with the best strategy to beat me. Okay, so this is clearly giving R an advantage. So this is saying that in the perspective of R, so R tries to maximize this problem by treating this X to be something that's fixed, and this is a linear program, right? So when X is fixed, X transpose P gives you coefficients of all the choices that you can make, and so among them, Y can choose the action, a single fixed action that maximizes the total payoff. So the objective function value is equal to this. Basically, pick your best action. So it's a straightforward optimization problem, because you can just go over the list and then choose the one that's largest. Then despite the fact that J disclosed his strategy, he still wants to win. He doesn't want to lose, right? So J want to somehow minimize the criteria, like despite the advantage that's given to R. Okay, so formulating that in an optimization problem is that J wants to minimize over this over all policies, over all probability distributions of choosing these actions such that this criteria is minimized, right? So let's say that in an alternative universe, and then the situation of the two players got toggled, right? So in this case, let's say R now gives J the advantage of disclosing his strategy Y like beforehand. Then like using the same logic, then then R can try to optimize his strategy by maximizing the minimum rather than minimizing the maximum. So R can now maximize the minimum, and clearly the minimum once Y is given becomes something that's as simple as this. You just choose a J that achieves the minimum. So minimax theorems. That starts from von Neumann and then later developed by a bunch of people, including computer scientists and economists and mathematicians. And remember, we talked about key fan in the context of fan-hope. So fan is also a great contributor to generalizing von Neumann's minimax theorem. So beyond this LP case. But what all minimax theorem is saying is that mean max is equal to max mean. So this is saying that no matter who gives the advantage to the other, like it doesn't really matter. So you guys can more or less just disclose your strategy altogether, and if you're playing conservatively, it doesn't really matter. You'll end up getting the same payoff. Okay. So that could be somewhat surprising, but I argue that this is actually just this is simply the duality and strong duality in linear program. Okay, to see this, let's formulate let's formulate the first problem as a linear program, and to make it simpler, let's introduce this additional variable to get rid of this maximum term, right? So recall that previously we have max I and P transpose X. We have this, right? So let's say that this is larger than T and convert that into a set of constraints. Okay, then this is an equivalent linear program that completely captures the solution of the previous one. And with this reformulation, we are now more or less in the standard form, and we can work out the Lagrangian, and then we can minimize the Lagrangian to get the dual function. Okay, again, by the mechanical calculation, we introduce a dual variable corresponding to, so to make it standard form, minus x smaller than 0. Okay, let's assign this dual variable u, and then for the and then for the equality equals to 1, let's assign this dual variable. Let's assign this dual variable v, right? And v is a scalar and u is a vector. And now for the last inequality, it's also we need a vector. Let's call it y, and then we get p transpose x minus 1 smaller than 0. And then we can just collect everything together and construct this lower bound of the objective function value. So we start with this, and then we minus the whole thing that by our condition that both u and y are non-negative, imply u and y being non-negative implies that this quantity is always smaller than 0. Okay, that gives the Lagrangian, and then we can minimize the Lagrangian. So the trick again is to collect the coefficients of x. So when we collect the coefficients of x, we get the py minus v, make it a vector, which is this vector 1, and minus u transpose x, and then we collect everything else plus t plus v and plus the last term involving t times y transpose with 1. Okay, so again, since we're minimizing this quantity, then the coefficients of x needs to be 0. Otherwise, we can choose x such that this function becomes negative infinity. So that gives us a constraint here. Okay, so yeah, so the primal is minimizing over xt. So all the so I guess all the coefficients of t needs to be grouped together as well. So we have this plus 1. Okay, so this term needs to be 0, and this term also needs to be 0. Otherwise, we can choose x and t such that the whole thing becomes negative infinity, and that gives rise to the two constraints. Somehow I think I missed the negative term here. I missed a negative sign here. Okay, so this to that, and setting this to 0, this to that. And when these two are satisfied, then all we are left with is just a single variable, single scalar v. Okay, so let's collect everything together to maximize this GUV function, and that would be to maximize v subject to the set of constraints looks like the following. But isn't this the same as the primal LP, except that we are maximizing rather than minimizing? Look, it's exactly the same, and y is restricted to a probability simplex, and then and then we and then we require this payoff matrix to satisfy that this v is always a lower bound of this payoff. Okay, so this so notice that this is exactly the same as the second problem. Therefore, like either by the minimax theorem we can get duality, strong duality, or by strong duality we can get the minimax theorem, and they are just equivalent in this case of the matrix games. All right, it's 2:05. We'll take a break for 5 minutes and we'll resume at 2:10. So meanwhile, if you have questions, please post your questions in the chat box, and I'll respond to your questions once I come back from the break. Okay, everyone, welcome back. Let's resume the lecture. Yeah, I realized that the reading materials for this lecture and the next are actually just a presentation slides. Are these lecture materials? So many of you who have already read the slides in details might find this lecture and the next like about materials that you've already read. Um, so um, so I hope that I can still provide like something new from my coverage of these materials to you in these two lectures. Um, Another thing that I want to point out is that the reason why I'm using the set of slides as reading materials, because this is really one of the best things that I like about Ryan Tishirani's version of um, the duality and also KKT conditions. Because in the Stephen Boy's book, so it doesn't really cover enough information. It doesn't even teach subgradients. That's why it doesn't have the generality that's needed to do like research in computer science and engineering. On the other hand, the other reference, common reference, the Rockefeller book. The Rockefeller book is more mathematical. It's in the convex analysis domain. It's very concise and very elegantly stated, and everything's compact and correct and elegant. On the other hand, it doesn't provide enough examples, and it also doesn't say things that maybe Rockefeller himself consider to be obvious. So to date, I think Ryan's lecture material is one of the best treatment of these topics in ways that are simultaneously insightful and mathematically rigorous. So that's the reason why I'm asking you guys to read the slides rather than read the book chapters. My boys' book chapters on these topics are just equally good and will cover some of the illustrations that in the Boyd and Vanderburger book like later, and we'll keep drawing useful materials from there. But do bear in mind that that book is usually like served as a handbook for practitioners to implement those algorithms rather than providing the sufficient mathematical foundation to do research with convex optimization. So to quickly summarize what we had, so we talk about the LP duality. We've provided two explanations. One is to use lower bounds by somehow matching the combine some linear combinations of the inequality equations or equations or inequalities in the system of constraints, so that we can recover the coefficients of the objective function value, and then if we maximize over those coefficients, then we can construct a dual formulation of an LP. The second explanation involving like they're essentially equivalent, but the second explanation is a little bit more general. That allows us to just take an arbitrary lower bound of the objective function value by adding something that's non-positive to the objective criteria. And that gives us the definition of the Lagrangian. And by simply solving the Lagrangian by minimizing over the parameter x, getting rid of the parameter x, then we get a lower bound that's then we get a lower bound of the optimal criteria value in the form of a function that's parameterized by the coefficients or the introduced dual variables on those constraints. Okay, and the optimization problem that maximizes the lower bound gives rise to the dual of an LP. So I talk about how this is actually the second explanation is more general and sometimes cover even non-convex ones. So let's let's now get to it. Let's present the primal and dual relationship in general convex program. Okay, so let's take the standard form of the convex optimization problem with HI being a sequence of convex functions and LJs being a sequence of affine functions of X. Like if when these are like convex optimization problems, then that's a requirement. F and H to be convex and L to be affine. But more generally, most optimization problem, like actually all optimization problems, yeah, I take it back. Most optimization problems, since these two are I guess finite. If this can become infinite, then that's all optimization problems can be written in this form, not just those convex ones. And for this family of problems, we can define the Lagrangian using exactly the way that we stated before. So we can write the Lagrangian as a lower bound of the objective function value at f of x by enforcing that the second part of this is always smaller than equal to 0. And for all the feasible solution x. Okay, and for all the feasible x, since we know that hjx is non-negative, non-positive, and lj is 0, we know that we don't have to place any restrictions to this vj, and provided that we ensure that this u is non-negative, then this becomes a valid lower bound of the objective function value f of x at any feasible x. Okay, so so take this one as an example, and how this actually applies to non-convex functions. Okay, so in this figure, the solid line is f. Okay, this solid line f. You can see that this f looks like it goes up and then goes back down, so it's not a convex optimization problem. And now let's also consider a feasible region of say minus 0.46 to 0.46. So in this feasible region, this function is not even non-convex. It might even be concave, right? So so we can construct the optimization the Lagrangian of this optimization problem by so this is I guess h h, this is h, and so what are else? Yeah, I don't think L is illustrated anywhere in this figure, but let's not worry about it. So let's say you just have one H and maybe you don't have L, and then by simply varying the value of U, and then this dashed lines, these dotted lines are Fx plus U times H of X. Okay, by choosing the different U. So when you can be by choosing like any u that's non-negative. When u is 0, then you get exactly f. When u is larger than 0, then you move more towards this h by having those right over there. Okay, so that will be an illustration. As you can see that within the feasible region, by adding this h to f, you always get a lower bound that supports f from below. Okay, so using the same argument that we had before, if we minimize the Lagrangian over either the feasible region or further relax it by minimizing that over everything, then we keep getting a relaxed lower bound of the optimal objective function value, since this is the mean of f of x. and then we can in the same way we can define this GUV more generally rather than just for LP. So this GUV is called the Lagrange dual function. So L is called Lagrangian and G is called Lagrange dual function. And this GUV always give a lower bound at F F star for any UMV that are feasible. Okay. So here's an here's an example. So the dash line is an optimal solution F star, and once you use this approach to construct a GUV, then you end up getting a function. So in this case, lambda is u, and there's no v, and so it's a univariate function that we can plot. And by just plotting this out, then you can see that this gives rise to a function that always lower bounds the optimal objective function value. Okay, so the Boyd and Vandenberger book, you can see you can see the exact function form of these functions. Okay, let's take some time to work out a few examples and how do we derive the dual and what this dual Lagrange dual function look like. So let's start with the simplest of them all. Let's start with a quadratic program where we want to minimize a convex objective function which requires this Q to be positive semi-definite. Okay, and let's write down the Lagrangian. So we first start by writing down the objective function, and then let's add let's make this x standard form. So you have minus x smaller than 0, and then with this we can assign the coefficient u to this inequality constraint, and then let's assign the variable v to the equality constraint of ax minus b equals to 0. Okay, so by doing this, and we can construct this terms that are always smaller than 0 by just adding them up. So we have u transpose x, v transpose ax minus b, and we know that this is always smaller than f of x, which is equal to just the first term. Okay, so how do we minimize this? So again, let's check that in the eyes of x, all the added terms here are linear in x, right? So all of these are just affine function of x, and since the objective function we know it is convex, then this doesn't really change anything. The whole thing remains convex in x for any fixed u and v. Okay, and also this is differentiable, so we can find the optimal solution to this by assigning the gradient to 0. So let's calculate the gradient. So the gradient, partial gradient of the Lagrangian. So by now, like you should be already pretty familiar with taking the gradient of a quadratic function. So we'll just write it out. Plus c minus u plus a transpose v. Right? So that would be the gradient, and assigning the gradient to 0 would give us I guess x give us x equal to q if q is invertible, q invertible invert q minus c plus u minus a transpose u. Okay, but q is not necessarily invertible. So notice that q is only positive semi-definite. Therefore, q might be invertible only in some restrictive subspaces. But what happens if q is not invertible, and then this vector happens to be in the direction that this equation cannot be true, right? So this is a solution to the linear system of equation of Qx equal to minus of this, right? Qx equal. So for any linear system of equation with this matrix Q, we can talk about when the system have a solution, when the system do not have a solution, and when the system have infinite many solutions. And in this case, when this term is not in the when this system is not in the span of that span the subspace of the columns of Q, then we know that the solution do not exist. And in the cases when these terms are in the when these terms are in the null space of Q and X, then there are infinite many solutions that we can use, right? Okay, so this so when Q is actually a positive definite, then this is a solution, and we can substitute this solution into here and obtain this. Okay, and this will be the dual optimal. This will be the form of the dual optimization problem. And notice that Q inverse is also positive semi-definite. Therefore, maximizing the negative of this quantity is a concave maximization problem or a convex minimization problem. So let's continue with the discussion of what if Q is not necessarily strictly positive definite. So in this case, we need to discuss whether whether this vector is perpendicular to the null space of Q, or whether this is inside the null space. If this is inside the null space, then if this is inside the null space, then we can always find an X such that we can get get the Lagrangian to negative infinity as we minimize X. Okay, so that happens here. And suppose this is actually perpendicular, then this is perpendicular to the null space. This means that this vector is actually in the span of the eigenvectors of Q that correspond to non-zero eigenvalue. Then essentially we can solve everything in the reduced space. Okay, and in that case, by simply replacing this Q inverse with Q pseudo inverse, solves the problem. Okay, so the trick to deal with matrices and to deal with the positive semi-definite matrices is always to diagonalize it, and by diagonalizing this Q into U lambda U transpose, then everything becomes on the it becomes very easily dealt with on the spectrum using this diagonal matrices, diagonal matrix of eigenvalues. Okay, just keep that in mind as you do the homeworks. Yeah, that's essentially all you have to know about linear algebra to be successful in this course. So let's continue with the example. And if we take a two-dimensional two-dimensional QP and then work out the energy landscape of the primal and the dual problem and plot it, then we can see that the primal and dual objective function actually hit the same location, right? So both the optimal solution of the dual and the optimal solution of the primal are actually at the same level, F star. Okay, so this is by no means a coincidence. We've already seen this in LP. But now, like seeing this again in QP makes us wonder whether the same condition of the so-called strong duality, where the dual variable, the dual optimal solution has the same criteria value as a primal optimization problem, like holds more generally for all or almost all convex optimization problems. Okay, so let's look at this problem in details, right? So notice that so the Lagrange dual exists for all problems, not just the convex optimization problem. However, like however, if in addition we assume that this is a convex optimization problem, then maybe we can get a little bit more than this inequality. Okay, another property that before we talk about strong duality and its associated condition is to think about is to think about what the form, what the property of the dual problem should satisfy. So even if the original primal problem is not a convex optimization problem, so we can see that the dual problem is always a convex optimization problem, even if the primal is not. So to see this, let's inspect the construction of this Lagrange dual function again. Okay, so this is GU of V, and then we are minimizing f of x, and with a bunch of other things. But so none of these needs to be convex. All right. But on the other hand, like notice that we only so this function is only parameterized by U and V. Therefore, in the phases of U and V, in the perspective of U and V, for every fixed x, this is actually an affine function. Yeah, just ignoring the mean x for now. This is actually an affine function in U and V. Affine function is the only function that's simultaneously convex and concave. Okay, that means that we can instead of minimizing this, we can add a minus sign and make this maximization, and then the whatever that's inside, we can treat it as convex. But pointwise maximization of convex functions is convex, right? So this is saying that ignoring this minus sign here, this max x part of everything ends up being convex, regardless of what f, hj, and lj nuclei. Right. So notice that we're maximizing GU and V. So having this minus in front of it is convenient. So we are maximizing a concave function subject to a convex constraint that says U is not negative. So this is fully general. It's saying that the Lagrange dual is always a convex optimization problem. So when you run into a challenging a non-convex optimization problem, so maybe a simple way to try out is to see whether there are interesting structures in its Lagrange dual, because Lagrange dual often provides you like a so-called convex envelope. It provides you an envelope that supports your optimization, non-convex optimization problem from below in the tightest possible way, which means that if you solve the if you solve the Lagrange dual, okay, if you start with the Lagrange derive the primal from the primal to get the dual, and then and then derive the dual again, dual of this dual, then often you'll end up getting an interesting convex relaxation of the original problem. In some sense, this is the tightest possible. And then by solving this, often you can recover the optimal solution of the original problem. If not, then it also serves as a reasonable approximation to the original problem, or may serves as a good initialization that you can do then use it to start your local search, like a gradient descent based approaches. Okay, so now let's give an example of the non-convex optimization problem in the univariate case. In which case we can see the details of how these things look like. So consider this function. So this is a familiar function from previously. When we like visualize when we visualize the Lagrangian. Okay, so it has this weird shape that goes up, goes down, goes up, and goes back down, and then up again. Okay, for a polynomial, like it shouldn't be surprising that you see functions with many bumps. Okay, so luckily, like for this function, it does admit like an optimal solution here. Like if we want to minimize this function subject to a constraint that x is larger than some quantity, and then we can then we get that that this point is actually the optimal solution of this problem. Okay, we can solve this since this is since this is a continuous differentiable optimization problem. We can derive the gradient, in this case the derivative, and we can also derive the second derivative. So by doing that, we can find all the stationary points for this problem by simply solving for all the roots. And then by evaluating all the roots that are enumerating the stationary points, and then by enumerating all the boundary points, including this one, and compare them numerically, then we can find the optimal solution to that minimizes this f of x. Okay, it has a closed form since we know how to solve a cubic equation, which comes out of the derivative. Okay. So so the dual actually look like the following, right? So we can visually inspect that this dual is a concave function. But like how do we see this algebraically? So to find J is actually like rather complicated. So it involves constructing the constructing the Lagrangian and then minimize the Lagrangian. So luckily the minimization of the Lagrangian remains solving a cubic equation, right? So we can solve that cubic equation and then work out that closed form. So everything's super tedious, but eventually we can end up getting the solution. We can end up getting solutions like having this form, and we can substitute this into the original Fi formula, and then that gives us this function g. But just looking at this function itself, it's really like difficult to see whether there are any structures that we can say about this function. But from the previous argument through convex duality and through the fact that the Lagrange dual is always a concave maximization problem or a convex minimization problem, then we know that this function needs to be not necessarily needs to be concave. Okay, so now let's talk about strong duality. So it turns out that for most convex optimization problems, strong duality is something that's given to us. So only under a very weak set of conditions called a constraint qualification. So there's a huge body of work on this problem alone. How do we characterize or find the set of convex optimization problems that satisfy the so-called strong duality? And there are many conditions that are proposed, and people are still coming up with like more general solutions or conditions of a different flavor. So Slater's condition is one of these so-called constraints qualification conditions. So it says that provided that your constraint set, so this feasible region of your convex optimization problem, have a point that's in the strict interior, then strong duality is true. Okay, so this is a relatively weak condition. It basically says that the problem is feasible, and not just feasible, it's feasible in the interior of the solution. It doesn't say anything about whether the optimal solution have the inequality constraint being tight, but it just says that there exists a feasible solution, which is often like very easy to construct. In addition, there's an important refinement of the Slater's condition that says that you only require these strict inequality to hold for some feasible solution for those function for those inequality function h that are convex but not fi. Like if for those functions that are fi, then you can get away with not having feasible solutions that not having feasible solutions that doesn't satisfy the condition that they are in the strict interior. Okay, so this is very general, but like if you want to invoke strong duality in your research, this is something that you need to check carefully, because in particular when you work with semi-definite programs, there are cases, there are like pretty pathological cases, but there are still cases where Slater's conditions are not true. Right, so maybe in those cases you want to check whether there are refinements or relaxation of this condition under which you can prove strong duality. And it's interesting. So what this is saying is that so this is a class of convex optimization problem, and this is a class of problems where strong duality hold. Okay, so Slater's condition provides a set of conditions under which it covers almost everything inside this region at the intersection of strong duality and convex optimization problems. So how to understand this set is still open. Like how do we characterize the entire subset of convex optimization problem that satisfy strong duality is still like an open research question, and arguably for practical reasons, like those are not too interesting. So they are mostly technical reasons. So in practice, at least like to based on my experience, like checking Slater's condition, I give you strong duality, and it's Slater's condition applied to your problem 99.9% of the time. Okay, so so the Slater's condition, especially its refinement, tells us something about linear programs. Okay, so notice that when the constraints are fi, so no matter whether it is, so it can be inequality constraints, you do not actually need a solution to be in the strict interior. Okay, so using that refinement of Slater's condition, that implies that all the linear programs, provided that it is feasible, then if the solution exists, then the LP primal and LP dual have the same optimal solution. Okay, so this is something that's extremely useful. So I encourage you guys to think about those cases when one of these problems are infeasible. So suppose the primal one is infeasible, what would the dual problem look like? And similarly, when the dual is not feasible, what would the primal be looking like? Okay, so we are approaching the end of today's lecture. So I'm gonna skip this example of support vector machine. So SVM is something that most of you might have already seen in the previous course, in maybe in optimization or in statistics or in machine learning. So so by working out the dual of support vector machine, that allows machine learners to do something very fancy called a kernel trick, right? So I'm not gonna be working this out, working out this Lagrangian and minimizing this Lagrangian for you, but because I think it's a good exercise for you to work this out yourself. Okay, but I do wanna make a remark about the form of the dual. Okay. Oops. So so notice that in the primal, we're solving this linear prediction problem. To generalize over the linear classifiers, so one trick that people use is to replace xi with some feature map of xi. In particular, you can collect xi square, maybe vectorized xi transpose, right? You can also so this is called a polynomial expansion. You can also you can also say that this phi of xi is a function. So this can be a function of exponential negative xi minus dot square, right? So this is saying that I'm measuring all points to by comparing its distance to this particular point xi. So in fact, you can solve something called the kernel support vector machine, in which case you are doing linear classification in this expanded feature space, and in this case, in this function space. And in those cases, the beta is a function, and it is a function, and then this phi of xi is also a function, and then this beta 2 norm square becomes the inner product of beta and beta in the that's defined in this function space. So often we want this function space to be a Hilbert space so that there's an inner product that's defined, and we can do this kind of calculations. So in that case, it says that we are kernelizing the support vector machine into a kernel SVM. And this kernel means reproducing kernel Hilbert space. So RKHS. The computational challenge that's associated with this approach is that now that beta is a function, then this is an infinite dimensional optimization problem. And how do we solve an infinite dimensional optimization problem in a finite computer? It's not entirely clear, right? But with a dual, so with a dual, if we look at what the dual look like, so the dual have the total number of variables that correspond to the total number of examples in your training data, right? So even though the primal is an infinite dimensional optimization problem, the dual is actually a finite dimensional optimization problem with size that's proportional to the data set. In addition, so if we look at this matrix, so this matrix is defined as follows. So it is a diagonal matrix, diag y, in our label by collecting all the labels. So this is a n by n matrix, multiply with x, where x is in a linear case, x has a dimension of n by d, and in the infinite dimensional case, x is in R n by infinity. Okay. So so then this matrix involves only calculations of XX transpose, and XX transpose is what we call a gram matrix. It can be written, so X transpose I and J can be written as XI transpose XJ. Okay, so each coordinate can be directly evaluated with the inner product. So in the kernelized version, so this simply becomes phi of xi inner product with phi of xj in a function space with this Hilbert space norm, and so by the way, this is equal to the integral over the Hilbert space xi t and xj t dt. Okay, and if you use a kernel representation, this simply depends on something that they can more easily calculate. So in the case of Gaussian kernel, so this becomes exp minus xi minus xj squared. So you can essentially construct this optimization problem exactly, and it is finite, and you can solve it. And at the end of the day, you can reconstruct the function by beta. And the predictions are also involving only kernel operations rather than anything that involves you to requires you to deal with the functions explicitly. Okay. So hopefully that provides a little bit of motivation for you to look at this example in details, because like almost all like linear methods can be generalized to kernelized linear methods. So there's a principal component analysis. There's a kernel PCA. There's a linear classifier, a linear logistic regression. There's also a kernelized logistic regression. There are kernel linear SVM and kernel SVM, and you can keep playing this game and come up with a lot of different kernelized methods that allows you to deal with nonlinearities and allow in a very principled way. And you put this is particularly helpful when nonlinearities are really what's hurting you in using your carry method in solving the problem. Okay, so finally, I'd like to talk about duality gap. So for problems where strong duality is true, then the duality gap, which is the difference between the primal solution and dual solution, will end up becoming zero when we substitute this x to be x star and uv to be u star and v star, and then we get a zero. And this can be quite useful in practice to certify to design stopping conditions for iterative algorithms. For instance, in gradient descent, one challenge is when shall we stop, right? So we talk about the criteria that requires a strong convexity. So when we have strong convexity, then the gradient, the norm of the gradient serves as a surrogate of the distance from the optimal solution. The duality gap, on the other hand, is something that we can calculate without requiring like strong duality. So basically just derives a dual, finds a feasible solution, and then takes the difference. And that will serve as a valid surrogate that we can often use in practice. Okay, we'll talk about it a little bit more when we get to second order methods, and also when we talk about stopping conditions in various iterative algorithms. And that's all for today's lecture, and thank you all for coming. And if there are any burning questions, it's a good time to ask now.
So I have a question because I'm confused about epoch and batch when I was doing homework too.
Okay.
So I don't know if you need to, if I should share my screen to show the homework too, or you have it.
Yeah, you don't have to. So when we refer to epochs, we're often referring to one pass of the data. So it corresponds to multiple batches, and each batch is like in some sense one mini batch. So that's one subsample of one random subset of the data set, and then for you to construct the stochastic gradient.
So like, for example, I want to run for one epoch, and that is a complete pass of the data set. But when I'm choosing the batches, if I choose them randomly, how can I make sure that it runs through all the samples?
Oh yeah, so it's an equivalent number of incremental gradient oracle calls that you have you have invoked, say you have a data set of size n, then n, and you have a mini batch size of m, then n over m would be the number of iterations or the number of batches that you need to take in order to get one epoch.
Okay.
It's just by convention, doesn't like come with any real significance.
Okay, just to make sure, like for example, if my data set, the sample size is 500 and my batch size is 10, so I just round 50 times and I select randomly.
Yeah, and then you can call that an epoch.
Okay, got it. Thanks.
Yeah, good question.